Friction is a force that we get whenever we have two materials either touching or rubbing against each other. The standard equation for friction is your normal force times your frictional coefficient. The frictional coefficient is simply a measurement of how sticky or rough or smooth the materials are. If something is very smooth and slick, like ice, you will have a low friction coefficient. If it's very grippy or sticky, like rubber or sandpaper, your frictional coefficient will be much higher. So to understand the equation for friction, we need to understand the normal force. The normal force is simply the force you get from a material that prevents you from breaking through that material when a force is applied to it. For example, if you're laying down on a piece of ice, you have two forces going on. Your force pushing down is your mass times your gravity. That's pushing you into the ice. The force pushing you up, that's your normal force. If you lay on the ice and you don't break through, that's because the force pushing you down and the force pushing you up are the same. If you ever see someone break through the ice, that's because the mass times gravity pushing them down was greater than the normal force of the ice pushing them up. So they broke through the surface. Most of the time on friction problems, your normal force is simply going to be equal to the mass times the gravity. That will happen whenever you're standing on a flat surface. If something is standing on an inclined plane, however, things can change. If I have this plane and I put a box on it, gravity is pushing the box down. The inclined plane translates that vertical force into a force going down the slide, but also into a force directly into the plane. The force that goes directly into the plane, that's going to be the source of my normal force. Your equation for a normal force on an inclined plane is your mass times your gravity times the cosine of the angle. And the cosine of my angle is just the ratio of the side adjacent to my angle divided by the hypotenuse. So if the sides of my triangle were 3, 4, and 5, 4 would be my adjacent side because it's the side touching my bottom angle. And 5, the slanted side, well, that's always my hypotenuse. So in this case, the cosine of my angle would be 4 over 5, which you could reduce down to 0.8 or 80%. So in this case, the slope of my inclined plane reduces my friction by 20%. So I only have 80% of my mass times my gravity. My final equation for friction would be my mass times my gravity times 0.8 times whatever frictional coefficient the problem provided. There are also two kinds of friction to be aware of: kinetic and static. Static friction is the friction that you experience before you start moving across the surface. So the two people on the left in this picture are both experiencing static friction because they haven't yet started to move. The gentleman on the right is starting to slide down the hill. Once he starts moving across the surface, that's called kinetic friction. The coefficient for kinetic friction is less than static friction. Once an object starts moving, it actually experiences less friction than when it was standing still. Just because an object is moving doesn't necessarily guarantee that it's experiencing kinetic friction. Tires or anything rolling are a notable exception. Clearly from this picture, we can see evidence of the tires scraping along the surface at some point. That scraping along the surface, that's kinetic friction. Most of the time, tires don't drag along the surface. Instead, they're rolling. Rolling is actually considered static friction. And that's because as the tire rolls along the surface, there isn't a point-to-point scraping or rubbing that you get when the car slams on its brakes and the tires drag along the surface. Another point of friction that can be confusing is the direction of friction. The direction of friction is going to be the opposite of movement. So in this case, we have a boat that's going to the left. Friction is working in the opposite direction, slowing the boat down. With rolling tires, the direction of friction can be a little bit misleading. As a car drives down the road, the tires are actually turning front to back. So the direction of movement with the tires is towards the rear of the car. Like we said before, friction is going to act in the opposite direction of movement. So in this case, friction is actually moving in the direction of the car. because it's not the car that's actually moving, but the tires against the road. And that's why, if you've ever seen a car on an icy surface, the car has a hard time moving forward. The tires spin towards the rear of the car, but there simply isn't enough friction from the ice to push the car forward. If you see a question on the MCAT about the direction of friction or about kinetic or static friction, it's most likely going to be about tires or a rolling vehicle. And that's because with rolling tires, it's so easy to forget that it's actually static friction and the friction is pushing the car forward instead of slowing the car down. An important fact about friction to remember is that friction does work. We usually think of work as doing something that increases the energy in a system. Actually, work is simply changing the energy in a system. So friction actually does work by taking energy out of a system. Friction usually takes kinetic friction and converts it into heat. If you see a problem where an object is moving and then somehow stops, most likely it was friction that took the kinetic energy out of the system. Here's a classic problem where friction is doing work. We have this hockey puck that begins with kinetic energy. Our kinetic energy formula is simply 1/2 times the mass of the object times its velocity squared. In this case, 1/2 times the mass of the puck that we don't know times 10 squared, or 100. So the puck starts moving, but eventually it stops. That means there was a change in kinetic energy, and whenever there's a change in energy, there's work being done. Our equation for work is simply our force times our distance. The only force in the problem is friction, and our equation for the force of friction is simply the mass of the object times gravity times the frictional coefficient. In this case, our frictional coefficient is 0.1. Because the object started moving and then stops, that means the work that's being done, or the energy that was taken out of the system, has to be equal to the initial kinetic energy in the hockey puck. In other words, you could say that the kinetic energy in the hockey puck, or 1/2 times the mass times 100, is equal to the force times the distance. And the force is simply the mass of the hockey puck times gravity, which is 10, times the frictional coefficient, which is 0.1, times the distance the object moves. We do some algebra, the m's cancel out, the 10 and the 0.1 cancel out, and the 1/2 and the 100 simplify down to 50. So 50 is the distance the object moves before friction can take away all of the kinetic energy.